Alright, so the suffix automaton, I'm going to do kind of a practical lecture because, to be honest, I just learned this week when I was working on some CSES problems. So I don't fully 100% like have an understanding of the algorithm to a point where I can explain it, but I do have an understanding of the data structure and how to use it, as well as like a rough understanding of the algorithm, enough to explain like why it works and the properties and things like that. So the suffix automaton, given a string, it is a partial DFA that accepts all the suffixes of that string. So for example, I've drawn the suffix automaton for BAA, BAA, and we can confirm that, for example, this suffix here, A, BAA, we take like A, BAA, look at that, we're at an accept state. If we take this substring, like I almost picked AA, which is a suffix, AB, for example, AB, not an accept state. Okay, this black marker is not very good, but you get the idea. Okay. So it's also a minimal DFA, which is pretty cool. So like this is the smallest DFA that has this property, which is cool. There are some guarantees about the size of the DFA. So there will be at most 2n minus 1 nodes and 3n minus, I think it's like 4 or something, like edges. So basically, linear number of nodes, linear number of edges, which is pretty cool. A little surprising, because you would think that it would be like, oh, you might need like n squared if all the different suffixes. But, I mean, as we've seen in other suffix data structures, suffixes have a lot in common with each other very often. The most useful property that isn't just the definition of a suffix automaton is that every substring in the string is like a path starting from the start state. So for example, the substring like AAB, you like traverse AAB and like that's in there. And there is no path in the DFA that isn't a substring. So every path in the DFA is a substring, every substring has a path in the DFA corresponding to it. So the way that we kind of like build the DFA, at least like naively, is you could consider for every substring, there is a set of end positions in the string where like that substring ends. So for example, the string AA, there are 2 positions where AA ends. It's 2 and 5. And for the string like BA, there are 2 positions where it ends. That's 1 and 4. Does that make sense? So then what we do is we define these equivalence classes. All the strings that have the same set of end positions are the same state in this DFA. So for example, the string BAA and AA, all instances of BAA end at the same place that AA ends in. We can see that because AA and BAA end at the same state. Similarly, like AB and BAAB, all of those substrings end at the same location anytime they show up. Does that make sense? Okay. Another thing is that the algorithm is online, so it's built by you're going character by character and adding them. So you just start with the root, which I guess accepts the empty string for the empty string. I don't know, it's like kind of useless. But then every letter you make a new node, which is the final suffix, which is the whole string, and then you do some stuff by like following the suffix links and connecting it into the graph. One observation that I made, an incorrect observation that I made is that I assumed initially that all the suffix links are like pointing to some node that's like has like a lesser value to you, so you can loop backwards to the nodes and all the suffix links are cool, but that's actually not true. So this algorithm works by taking a node, following suffix links of the previous node until it finds something that has the transition, kind of like Aho Karasik or KMP, and then it directs that.
I didn't get that.
Okay, thank you, Siri. So it finds a node that can connect to it, connects it, otherwise it's like the root. And it also duplicates a previous node so that it's still there before the suffix exists, and then it reconnects the whole graph like that. I won't go into details about the algorithm itself because it's not useful, and I've found that you don't need understanding of the algorithm itself to solve problems with the suffix automaton. One.
Are we saying the start state is an accept state?
I mean, the empty string is the suffix of a string.
Well, yeah, but then we have like the string BB. I think that gets accepted.
No. Where's BB?
Like that transition back to the start node.
No. Okay, yeah. So these red edges are not DFA edges; these are suffix links.
Oh. Okay.
So yeah. So where I was going with that is, yeah. So we have the DFA, and that's in blue, and then every node has a suffix link, which is for this state. Basically, like we can say a state represents the longest like path that gets to here. So this state is like, you can take AA to get here, but you can also take BAA. So this state's length is 3. We're gonna call it 3 because that's the longest way to get here. And so really the length is just like the length of this, because every node is either created by like adding a new letter or cloning an existing state. And if you clone an existing state, it's obviously going to have the same length. And if you create a new length, if you create a new node, then you're going to have a like length plus 1 of the previous or whatever like that. So this has a length 1, 2, 3, 4, 5, 6. And again, this is 4, even though you can get here in 2, the length of this is 4. Seba?
Can you build this like online?
Yeah.
Okay.
This is built
like
online
okay,
character by
okay.
character, yeah.
I don't know if this is dangerous to view it this way or not, but could you use this as a NFA where suffix links are epsilon edges? No, I don't think that
I wouldn't really
no, that doesn't
know
make
if you
sense.
would want to do that. Yeah, so the suffix links are for this node. There is like a substring of the string that is like the longest one here. What is the longest proper suffix of that string that is in a different equivalence class? So if we look at the string BAA, the proper suffixes of that could include AABAA. So you're like, oh, the suffix link of that should just be, or sorry, the suffix is like, I don't know, whatever. Yeah, that's a suffix. But the thing is, like AABAA, every time you see the whole string, you also see AABAA. So they're in the same equivalence class. They're in the same node. So it's like so the suffix link isn't there, and so it turns out that actually the longest suffix of the whole string that isn't in the same equivalence class is BAA right here, and we do this for the entire thing. So in my implementation of the suffix automaton, which I try to get as short as possible, it's like 150 characters shorter than suffix array, and it's also a lot easier to type because there's less symbols and more words. I found that when I type it, it flows better as you type, and it's like harder to make bugs. Whereas in the suffix array code, I mean, how many of us have made a bug while typing suffix array code and the hash doesn't work and you have to go find it? I mean, maybe it's just me and Cam, but it does happen. It does happen. So this code is easier to type. It is also a fair bit shorter. Yeah. So let's go ahead and figure out some problems we can solve with this. I'll go for the first problem. Oh yeah, Safik.
So if all the suffixes of something all end up at the same equivalence class and position doesn't have a suffix link?
Well, suffix links to the empty string,
Oh, okay.
which is the root. So it does.
Wait, so two strings are in the same equivalence class if they like occur at the same places in the string, or like?
Yeah.
I think another way to think about it is that like if you make like the suffix try, like if you made a try out of all the suffixes, two nodes would be in the same equivalence class if their like subtrees are the same.
Yeah. Yeah, which would basically be so like I've seen this compared to on Code Forces as like an even further compressed suffix tree. I haven't really thought about that too much, but I suppose that kind of makes sense. You take the suffix try and you compress all those nodes that have the same thing.
It's like a suffix tree, but compressed on the nodes instead of on the edges.
Yeah. So this has a lot of similar properties to suffix trees, but not all quite the same. Okay, so let's go ahead and for perhaps the easiest problem is you're given a big block of text and a bunch of queries, and for each query you want to determine if this string appears as a substring in the big block of text. Does anybody have any ideas of how to solve that?
Process this, see if the query string just leads you to any valid state in the suffix automaton when you start it.
Yep. So as I said earlier, every path in the DFA corresponds to a substring in the string. So what we really have is we build the suffix automaton on the big string, and if we want to query if a string is in the text, then we follow that string's path in the suffix automaton, and if we ever like try to take an edge that doesn't exist, then we know that that string is not a substring of the original string. Are we all on the same page about that? What?
That's unrelated to the accept states, right?
Yeah, that's unrelated to the accept states, because the accept states
Are
are,
they at the end of the string?
what?
Are the accept states at the end of the string?
The accept states are suffixes. So the definition of a suffix automaton, I think you walked in a little late. The definition of a suffix automaton is a partial DFA that accepts all the suffixes of a string. So yeah. What if, oh, go ahead.
Wait, you said that a string is a substring of the like big string if you don't like step out of the DFA while you're walking through it?
Yeah, if and only if.
Okay.
Yeah.
That's pretty good.
So that's a nice bijection. What if you wanted to count the number of occurrences of a query string?
This guy is out, dude. He's not good.
So right now, like if you wanted to count the number of occurrences of a query string, perhaps before, like a week ago, I would have built Aho Crossic on all the query strings. Actually, a week ago, I did. I solved this a week ago on CSES. I built the Aho Crossic on all the query strings, like the dictionary, and I traversed it with the text, and then I did like the suffix link subtree sum. But with the suffix automaton, how could we determine the number of occurrences of some string in the text? Andy?
Suffix links.
Okay, so just suffix links in the AC. Nice.
Suffix link point to it.
Gotta respect.
Go ahead.
Like number of nodes that point to it through suffix links.
The number of nodes that point to it through suffix links.
Yeah.
Suffix links of what? Just like it?
Like that. Like if you follow the suffix links backwards, the number of nodes you can reach.
That's actually really close. So one of the ways of implementing this, it requires a little bit more about like knowledge about the algorithm itself. But basically, like I mentioned earlier, whenever you make a new node, you either are making it because you're adding a new character, so you need that like full suffix to be like in the DFA, or you're cloning an existing node. So the first time I implemented this algorithm, it's you want to know the number of non-clone nodes that are in your suffix link subtree, and that's basically the number of suffixes that point to you.
Oh.
And they might not be pure suffixes of the entire string, because like they were suffixes at one point in time, but now they're not, because as you added more things. But at some point they were suffixes. So if they point to you, that means you're a suffix of something that used to be. You're a suffix of something that used to be a suffix, which is something that used to be something that is a prefix, which means you're a suffix of prefix, which means you're a substring. Seba.
The suffix links still form like a tree, right?
Yes.
Yeah, but it doesn't work because it's like then some node can represent multiple suffixes.
Yeah. So then you have to have, and it's not hard to do in the code. The code that I have actually maintains that. But yeah, it's you just need to maintain whether or not a node was created as a clone or as like a new node, and then you want the suffix link subtree sum of the number of non-clone nodes. There is an easier way of doing this though.
Can you like figure out for every node how many suffixes it represents? I mean, like.
Yes. So if you're at some node, let's say that I'm at this node. I'm at here. What is the number of suffixes I can reach? And I'm talking about true suffixes. So like, this is a true suffix, this is a true suffix, this is a true suffix of the entire string. Not like it used to be a suffix, but then you added more characters. So basically what you can say is the number of occurrences is the number of paths starting at U that end at an accept state. And that is basically saying, okay, well, I'm at some node, that means I'm a prefix of the string, right? And I want to know the number of suffixes that contain this prefix, which is basically saying if I started at this substring, could I go all the way to the end of the string and still be like good to go? So you can do this with like a pretty simple DAG DP. So for this guy, his answer is whether or not he's in accept state plus the sum of all of his children's DP values, and you do this DFS as a DP, and you're good to go. Are we all on the same page about that DP? Because that's like the classic. We're gonna need to understand that for all of these algorithms is that DP.
this DP solves for what?
This DP solves for some node. What is the number of paths starting at this node that ended in an accept state?
Yeah, or what is that counting? It's like the...
That's like the number of times this is a prefix of a suffix.
Like the number of times it's a substring.
Yeah. But specifically like how we got there, because remember the accept states are that's saying, oh, this is a suffix. So if we can walk from myself to an accept state, that means I must be a prefix of a suffix of the string. Right? So we want to find, if we want the number of occurrences of a prefix or of a substring, we take that substring as a prefix and we find the number of suffixes that it is a prefix of, which is the number of substrings.
And this DP doesn't use the suffix links, right?
That is correct. You maintain a suffix links mostly because of the algorithm's internal workings, but also it's like very easy. Like you can't really maintain the accept states as you're building the tree, or sorry, the automaton, because like something that used to be a suffix, you add another character to the end of a string. Now nothing that used to be a suffix is a suffix anymore, right? So it's kind of like all really wonky as you're adding new nodes and you're shifting around the entire automaton. It's still in your time, but it's like you're making a lot of changes. But what's nice is if you just keep track of the last node, which is already maintained in the construction of the automaton, you maintain the last node that you added that wasn't a clone, then you know the last node that you ever added as not a clone is the entire string as a suffix. And so you take all of its suffix links and you mark that as accept states.
Because the suffix link is like removing one character, right?
Well, it could be removing multiple. It's a suffix link is a link to a node that is a suffix of you, but in a different equivalence class.
Because in a suffix tree, it's like removing one character, but here it's not.
Well, in a suffix tree, it could be removing multiple as well, right?
No, I don't think so. I think in a suffix tree, it's just like take the first character off.
Okay. Okay. Well, this could be removing multiple characters. As you see, because we have a 6-character string, but our suffix link path is length 3, so we have to be removing multiple characters, pigeonhole or something like that. Okay, so are we all on the same page about this DP for like finding the number of paths from some node to any accept state?
What node did you start on?
Any like this DP is for doing this for all nodes.
Yeah, but like if you're finding the number of occurrences of one substring,
Yeah.
which node do you start at?
So you traverse the DFA for that substring. So for example, the number of occurrences of AA, we traverse AA, and now we want to find the number of paths from this node that end in an accept state.
Okay.
So it's 1 because this is an accept state, so you could just stop here, or you could go further and there's another accept state.
Okay.
The number of times that A shows up is going to be, okay, we traverse A, and then it's like the number of times we can get to an accept state, which is 1, 2, 3, 4. Does that make sense? And as you can see, the number of A's is 4. Okay, same page? All right, what if we wanted to count the number of distinct substrings in a string? Just gonna see if anyone has any ideas. Right.
Isn't that like the number of nodes in the DFA?
No, it's not the number of nodes in the DFA. I don't know the number of distinct substrings off the top of my head for BABA, but I doubt it's this. If it is, that's crazy. Eddie.
Number of paths?
Number of paths. So as I said before, every path in the DFA corresponds to a substring. So if we know the number of paths in the DFA, then we know the number of distinct substrings. And we can do that with another DP. It's pretty similar to the previous one, except instead of saying we like +1 for a node that's an accept state, we just +1 for any node.
I'm assuming we mean simple paths here.
Well, there's no cycles.
Well, in this one, but could there ever be cycles?
There will never be cycles.
There will never.
There will never be cycles. Because if there's cycles, that means the string has infinite length.
Sure. Yeah.
So that's obviously not true. So no cycles. Good question.
Wait, this is counting the number of simple paths from the start?
Well, I mean, you want the answer would be from the start, but like you do the DP for every node, and then you can answer queries of like, given like what's the number of distinct substrings that start with this, just by traversing to that node in the DFA and then saying, all right, what's your DP value? Okay. Or you just
I'm sorry.
just chilling? Okay. Any questions about number of distinct substrings?
Wait, what's up?
Any questions about number of distinct substrings?
So it works because there's exactly like a one-to-one mapping between every substring and every path.
Yeah. So there's a one-to-one mapping between is it a substring and there is exactly this one path in the DFA that maps to that substring. And if there's a duplicate substring, it would be the same path. So if you're counting number of distinct paths, number of distinct substrings. Cool. All right, what if we wanted the kth lexicographic distinct substring? So if you took all the substrings and you distinctified them, then what's the kth lexicographic one? How could we do that, perhaps? One.
We like do the DP where it's like number of paths, and then it's like we like try taking you said the smallest?
Yeah, smallest.
So like we try taking like the smallest edge that we have, check if like that's like leak with a K or Greek with a K. And then if it's not, we like subtract that from our K and then check the next edge and do that type of process.
Yeah, perfect. So it's kind of like the segment tree walk where you want to find like the first prefix that has like a sum greater than x. So you check, oh, should I go to my left child? Is his sum greater than x? If it is, then I should go into him because my answer exists in there. Otherwise, I know it's in my right child, and I have to subtract k from, but I have to subtract my left sum from k. It's basically the same thing where you run the number of paths DP, and then you're saying, okay, if I'm at some node and I need to like find the kth string. Well, let me look at my a edge. Okay, well there's 10 paths that reach, or there's 10 paths starting from that node. But if k is 20, then I know that like, oh, I don't need to go into that node. So let me go to my B edge, we go to my C edge, and we go to D edge, and so on and so forth. So yeah, great job. That's good with that.
Yeah.
Pretty good.
Let's go.
What if we wanted to find the kth smallest substring, but we're not removing duplicates. So just kth smallest substring, but duplicates are like cool. We take those.
Aren't you doing like the same DP, but you have to do the pre-comp where it's like for each node, it's like the number of times you visited, like the thing we were talking about before, where it's like for each node you like calculate how many times you visited in the original string, so that way you know how many like times you visited, and then now that like weighs your path because like for each path you know how many times it appears in
So
the
it's
original.
like how many, it's the same as like how many final states you can reach.
Yeah.
Yeah.
Yeah, so it is essentially the same problem. Whereas instead of saying, oh, if I consider some edge, what's the total number of paths out from that edge? It's really what's the number of paths that reach a suffix, which is an except C. So very, very similar code, slightly different implementation about whether or not we care about is this the node or is this the terminal node, and then it's basically the same thing. Okay, let's see. Yeah, catch string substrings, k substring. All right, what if we wanted to find the shortest missing substring? So given some prefix, we'll just start out with yeah. We have the string. What is the shortest string that is not a substring of the whole string?
Another
C. Okay. Well, alphabet is A B.
Oh, dang.
Okay. Yeah. I bet we could do some DP where we either go down one of our like children edges, or we have some character that is not an outgoing edge from us, and we can step out of the DAG.
Yeah. What?
Yeah. I think you've asked me this before.
I
It's
did,
like-
but you did it on a suffix try or a suffix tree.
Yeah. So like, if a node doesn't have an edge, then you consider that like the next, like any letter, or like that means that like you could make a substring with one more character.
Yep.
So you can like set that node's value to like 1.
Yep.
And then you do like the DAG DP where it's like the min of like the edges you can take plus 1.
Yep, exactly. So just to reiterate what Juan said, if you're at some node and it's like missing an outgoing edge, like from the alphabet, so like if the size of its adjacency list is less than the size of the alphabet, then the answer is 1, because you know you can just take one more letter and you get to a substring that's not in there. But if you have every outgoing edge, then you do this like DAG DP, where you take the min of all of your like children's answers, and then you +1 that, because you're adding one more character to get to that min. So again, yeah, Zach?
I'm confused why you need to do a DP rather than just like a BFS.
Yeah, so if you look at this path, for example, you see how we can get to the same node multiple times?
Mm-hmm.
So that'd be problematic if we were just doing like a BFS, because then we'd end up like running the same DFS or BFS from here.
Well, you could just like mark it as visited, right? Because you only care about the shortest.
Well, that's a DP.
No, I mean, it's not like BFS.
I mean, yeah, like when I coded this, it's a DFS or a BFS or whatever. But you have to have the market as visited, but that's what a DP is. So, because you also, like, for that node, you save its answer. So you end up coding a memoized BFS, which is a DP. So, yeah.
Makes sense. It's like you BFS to the first guy that has like a missing outgoing edge.
Yeah.
Also, the answer
Well,
is
okay.
almost log, right?
What?
The answer is almost log. And that's
Yeah, but like if the alphabet's quite small, then like you could have a very large answer, and you're gonna end up like you're gonna have a linear thing. And so we can take this a step further, where we have queries of I put this problem in the Discord. We have queries of like your cat ran across your keyboard, and you can't hit backspace, but you still want to type the shortest missing substring. What's the number of characters you have to type to get to a missing substring, given this prefix that your cat typed already? Does anyone have an idea for that?
Wait, I thought you were saying that like suffix structures was like overkill for that.
No, but like I didn't say that.
Oh,
Like
I- 'cause
suffix
I was
tree
like,
is
I was-
overkill.
I mean, it's like the same thing.
Well, yeah, it's just more code. But also, you volunteered that. Like you're like, oh, talk myself down from the suffix.
Well, yeah, like I feel like there's like a none of the above.
Yeah.
Kinda.
I mean, maybe, but.
So the first thing that like you can observe is that if you're forced to take a certain amount of string, you're gonna start your start state and then go through that string, and then whichever node you end up at, that's where you're gonna start processing things.
Yep.
You also have to handle the edge case that the string that your cat typed in already doesn't exist, which you can do through the simulation.
Yeah, it's the same thing. Whereas as you're traversing the
Yeah.
DFA, if you try to take an edge that doesn't exist, then your answer is 0. Cool. You already found a missing substring. Andy?
okay, but get this.
Get
Given
this.
a bunch of queries, outlaw, lexicographically smallest, minimal, shortest, minimal, shortest, missing substrings, substring.
Does that be short?
Shortest, yeah, shortest first lexicographic.
Alright, easy. BFS.
We got persistent suffix automaton. I don't know. That'd be kind of funny. I wonder if you can do persistent suffix automaton.
That was a problem once that.
Oh gosh.
But it was like, so it was a problem on, I think it was like 2019 or 2020 Latin America regional. But then like the author was just like, oh yeah, we'll do like persistent like suffix like, I think it was suffix automaton instead of like suffix tree. But like it's not actually, you can't actually do that, cause it's like it's not, like adding a character is not true of one, it's like amortized of one.
Yeah, that's, yes.
Yeah, and so then, so they did that, and then like, after like publishing this contest, which was like a regional, like they got like hacked in the comments, which is really funny. But you can actually solve that problem, it's really cool. That's like one of like the coolest problems I've found, is like, yeah, like.
Monkey's keyboard?
No, not Monkey's keyboard. Monkey's keyboard's goated with the sauce.
Okay, so back to. I'm gonna cut the stack off there before it gets any deeper. Yeah, so back to the suffix automaton. There's one more thing that's super useful to maintaining your suffix automaton, and that is the position in the original string that this node corresponds to. So when you make a new node, like as I mentioned earlier, we're always maintaining the length of a node, which is the length of the longest path from the root to here, and that's very useful. But we can also maintain the position of like some position in the string. I think it's the first where this node like occurs, and the way that we do that is if we make a new node, well then its position is equal to its length minus 1, because 1 like 0 indexing. Does that make sense? And if we ever clone a node, then its position is a copy of its clone's position. So basically now we can maintain, so for example, this node here would be like 0, 1, 2. That's like that would be its position would be 2. Its length would be 3. This node here, its position would be actually, it might just be 2, but it could also be 4. I actually don't know. I would have to see how that node is exactly generated in the Suffix Automaton code. I think that's not a clone node, so I think it'd be 4. But I don't remember. But it's maintained in the Suffix Automaton. So we have the position. So for example, if we wanted to find for some query string, where is the first time it shows up in the text? How could we do that? This is not a trick question.
You can walk the DFA.
Yep. Walk the DFA, and then once we're at the node, we know the answer. It's in the node. So I guess then this position would be 2. Yeah. Qual.
Does your code already do this? Or
Yes, it does do that. So the code maintains the length, the position, and then whether or not it's a terminal node, and then the rest of everything can be done with a relatively straightforward DP. So like whenever I need to do a DP, I just add like an additional like int DP equals -1 into the state, and then I'll just do DFS, and the DP is relatively
By
straightforward.
terminal node, you mean accepting state?
Yeah. Okay, so let's see. There was a problem on the Codeforce's suffix array edu called refrain, where a refrain in a string is every substring is a refrain, but the value for some refrain is its length times its frequency. So the number of times it shows up, and then the length. So for example, the longest or like the best refrain in this string would be BAA, because its length is 3 and its frequency is 2, so that's a product of 6. Whereas if you just took AA, for example, that shows up twice and its length is 2, so it's meant to be 4. A would be, it shows up 4 times, but its length is only 1. So the answer for that would be 4 as well.
And do the whole string as well?
Probably, yeah, I think so.
And then you want to find the maximum refrain.
You want to find the maximum value of refrain, as well as print that value, print the length of the refrain, and print the refrain itself, the substring.
So we already have a way to get the number, or wait, what? We already have a way to get the frequency of every substring, every node.
And how do we do that? Just as a reminder, a recap.
It's the number of final states the number of paths to a final state.
Yep. Yeah, so it's the number of paths to a final state is the number of times this node shows up.
And then we also have the length.
We also have the length.
The longest thing there. So I think we can multiply those two values and take the largest of them.
Yep. That's pretty much it. So like I said, this is like pretty straightforward. If you were trying to do this with suffix array, it's kind of like you do like some DSU or like range merging stuff on the LCP, and then you have to like, as you're like merging these like ranges together, you like maintain the whole thing. But with the Suffix Automaton, it's less code than suffix array, and it's also like 2 lines of code, which is for each node, take its DP value, multiply it by its length, and max that with the answer. And it's like so simple, and then once you find the answer, you also just maintain the node that corresponds to it, because that node also has the position. So if you want to find the substring, you just say like str.substring, that position minus length minus 1, and length, and there you go.
That'd be kind of cool.
So that's pretty cool. What if we wanted to find the longest repeating substring? So this is a problem with CSCS, but you can take it a step further. It's like, we want to find a substring that repeats at least k times, and we want to find out of all those substrings the longest one, and print out the actual substring.
Wait, a substring that repeats at least k times?
Yeah.
And the longest one?
Yeah.
So phone a friend. Or
Oh, okay, so it's like, we only wanna check the nodes, like, once we do like the frequency thing, like how many substrings in that node, and we wanna check the nodes that are like equal to K. And then so like, and then so like, then we like find the longest path that goes into that node.
The longest. Oh yeah, but that's already maintained in the node. Is
Oh,
the
sure,
length of
sure,
the node.
whatever.
Yeah.
Yeah.
So again, doing this with suffix array would be kind of annoying. Like you've got these like you want like the not like times like the LCP is like shows up at least greater than this number of times, which you have to do like a 2-pointer sweep or something like that. But with suffix automaton, it's no problem. All that information is stored in the suffix automaton once you do this 3-line DP to find the number of terminal states you can reach, or the number of paths to a terminal state. And so, yeah, like Juan said, for each node, if its number of paths is greater than or equal to K, then you max that with your answer, and you're good to go. Okay.
I think you could also build the suffix array from the suffix automaton.
Yeah, I was thinking about that. It's, yeah, I was.
Use dollar sign or something, and then use it like that.
Dollar sign.
Gotta respect it.
I don't know. Maybe, it's probably possible.
Suffmaton?
What?
Suffmaton?
Suffmaton?
Are we just? Oh.
Yeah, I've seen this acronymed as SAM because SA is already there, and this acronym is SA, but SA is suffix array, SAM is suffix automaton.
Nah, I would play suffix array.
I mean, honestly, based. No, not every problem with suffix array would be more easily solved with suffix automaton. But what's cool about suffix automaton is it solves problems that would otherwise require suffix array or aho-karasik or some like binary search hashing stuff like that. It's shorter, it's asymptotically faster, and also wins in a lot of benchmarks. Probably, like I ran 2 problems, or like every time I submitted a suffix automaton solution to like a problem I had already submitted with suffix array or aho-karasik, it was like a lot faster, which is pretty cool. It's 150 characters shorter, easier to type, less bug prone, and it's hipster as fuck, which is nice. It's definitely gangsta.
It's just to steal your girl.
Yeah, I mean, all I'm saying is it's pretty cool.
Pretty cool trick.
Yeah, you can also do like longest common substring between 2 strings by saying, okay, well, I'll put the suffix automaton on like the first string, and then for like every character in the other string, I'm gonna like try and take a down edge with this node, and if I can't, like with what I'm like maintaining what node I'm at, try to take a down edge, and if I can't, then I suffix link up until I can, or until I'm at the root, and then if I can take a down edge, so I'm also gonna maintain the length of this match. And every time I take a suffix link, I'm gonna like set my length to that node's length. And every time I go down, I'm gonna increment my length by 1. And so like I'm gonna like suffix link up, and then like maybe make a couple matches, increase my length, and then maybe suffix link up after I find some other characters in the 2 strings. Yeah, it's kind of like KMP but more complicated. I mean, yeah. But what's also cool is that, so I have not confirmed this or coded it up, but I think it should be possible to do the longest common substring between like a bunch of strings by, if you build the suffix automaton with like a separating character in between like all the strings, then every time you finish one string, you like go up the suffix link path and add 1 to like, oh, this is the number of times I'm a suffix of one of the strings in my set. Then, after you've done all this, some of the nodes might have an answer of like the number of strings that there are, which is like, I'm a suffix of everything. And then you want the longest node that can reach one of those really cool nodes that's a suffix of everything.
Yeah, Sharon talked about this when he talked about like suffix trees a while ago. It's like the same idea. It's like you do like the separating characters, but then it's like you pretend like they're distinct.
Yeah. Yeah, which I think should be pretty simple, just by like, okay, add them, and then you restart your like current node at the root, and then like just take some random edge, some like random node that doesn't exist.
What are you using the separating characters for?
So it's like the as we generate the okay, I'm just gonna leave.
Guys, pretty.
Yeah. So as we're generating the suffix automaton, we have this, it's like the online algorithm. So we're doing character by character. But we can also say like, okay, we could just add an extra loop on top of that, which is for every string, add it, and then say, okay, now that we're done, we're gonna do like the suffix link path from like the last node, which is like the suffix, the actual entire string for this string. All of those suffixes are like +1, and then you like restart at your root, and then you take some like edge that doesn't exist as like not a character that you've ever seen before, which you can just like, you can do that like instead of a map of characters to nodes, it can be like a map of ints to nodes, because this algorithm does not care about the alphabet at all. So you can just do like whatever 1,000 plus n or something like that, and then now you're at some node that doesn't exist as an alphabet anywhere else, and then you keep doing the same thing, and eventually you probably would converge to a node that suffix links to something else from like a previous string. So like if all the strings ended in B or whatever, then you might just end at some like thing which like suffix links to B, and then like that guy would be cool.
I have a question about the automaton that you have drawing out. Is there supposed to be a suffix link from on the top node,
Yeah.
third from the left?
Yeah, I think that's suffix links.
I think that should go back to the beginning.
Let's see here.
Oh, here. Okay.
Thank you. Yeah, I think that's all I've got. I can put my most recent code in like the algorithms, and I'll probably work on like a hackpack PR for Beehive, and then you guys can just copy that file from the Beehive hackpack once I have it.
I just like didn't understand what the equivalence class was.
The equivalence class is for a set of strings, or for some string, you can like enumerate what you could imagine, enumerating all the positions in the string where this substring ends. So for example, for AA, it's 3 and 5, because AA ends here, or I guess it's 2 and 5, it ends here and it ends here. And two strings are said to be equivalent if their end position sets are the same.
So BAA also ends in the same place. That's why BAA and A end in the same node.
Yeah. So every time you see BAA ending, AA also ends.
But A would not have the same equivalence class.
That's correct. So A is not the same equivalence class because A ends here as well as here, and here as well as here.
So if you like compare two strings in the same equivalence class, it's like one is a substring.
Suffix, actually,
Suffix.
which is even nicer. Yes, so two strings that are in the same equivalence class, the longer one contains the shorter one is a suffix. And so if you have like all of them, then you could like sort them. Imagine sorting them by their length, suffix, 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 all the way up. So like this node contains 2 substrings. No, 3. There's 3 suffixes that end here. It's the whole string AABAA and ABAA, all of which only end there. And as you can see, those are all suffixes of each other. And then the suffix link here says BAA, BAA, which is like this one, or it's just BAA. But also check it out, it's AA ends in the same place. So, and there's a path from AA to here. And the suffix link of this guy is A, and the suffix link of A is the root. Yeah.
Wait, just want to clarify something real quick. The suffix link connects you to, it's the longest substring that shares the equivalence class with that node. So
The longest substring that is a suffix of you, but doesn't share the equivalence
doesn't.
class. Yeah. Because otherwise your suffix link would be to yourself. Because
Okay.
that's what a node is an equivalence class. Any further questions?